So metallic bond क्या है? In metals, atoms closely packed होते हैं, so much so they are touching one another when they are vibrating in a to and fro motion, and they are together in a regular arrangement. We call that regular arrangement as a lattice. Metal atoms in a lattice tend to lose their outer shell electrons, and all of them do. So basically, they are not atoms. It's better to call them metal cations or metal positive ions. Outer shell electrons occupy new energy levels and are free to move throughout the metal lattice. This is something which was not considered so much as written in the book in previous years papers. फॉर एग्जाम्पल अगर आप आज से पिछले 2-3 साल के पेपरों में जाएं तो ये पीस ऑफ इंफॉर्मेशन मैनिपुलेट किया हुआ है. उससे ज्यादा पीछे जाएं 5 years, 8 years, 10 years पेपर्स नहीं मिलेगा. ठीक है. सो दिस इज समथिंग दैट इज वेरी इंपॉर्टेंट ओवर हियर कि आपके पास जो एनर्जी लेवल्स बिल्कुल आगे के होते हैं, बिल्कुल फ्री होते हैं, एम्प्टी होते हैं, और हम इमेजिन भी नहीं कर रहे होते कि वहां पर इलेक्ट्रॉन्स आएंगे. वहां पर इलेक्ट्रॉन्स आते हैं, और वहां पर इलेक्ट्रॉन्स आने के बावजूद वो फ्री होते हैं टू मूव थ्रू आउट द लैटिस. उनमें एंटर होना और उनसे लीव करना इज लाइक ऑप्शनल फॉर देम, ऑल्दो इट्स नॉट रिटन क्लियरली ओवर हियर, लेकिन हम बच्चों के लिए ये बताते हैं. Right? So we call these electrons as delocalized electrons. We call them mobile electrons. We call them freely movable electrons. All of these words are correct, but we prefer our students to write the exact word delocalized. It's better than writing using the term mobile. Don't use that, since that's more of a childish word. Or freely movable electrons is also a childish word. So use delocalized. Delocalized are electrons that are not associated with any one particular atom or bond. So that's why we call them delocalized, since that they can move around the whole structure, through the structure. अभी diagram आ रही है, इसे हम ज़्यादा अच्छी तरह से clear करेंगे. Metallic bonding is strong. Ions are held together by strong electrostatic attraction between positive charges and negative charges of the delocalized electrons. And here we go, we have the diagram over here, which gives us a very good idea how they are properly arranged in patterns, how they all tend to lose their outer shell electrons, how they all become positive ions, and the electrons become delocalized electrons and are attracted by anything in the area, any ion in the area. Now, there are a few things which we need to understand. In A levels, examiners assume that you have done it from IGCSE, and I usually explain to IGCSE students of mine, but I don't know whether you are up to par or not. So I'm going to explain a little bit of IGCSE part over here. All right. So when I talk about metals and when I talk about their structure, the first thing that we usually say is that they are solids. All of them are, except mercury, of course. We usually say that most of them are hard, some of them are soft. We give the exception for group 1 metals. We usually say they are dense. Again, the exception for group 1 metals. We say that they have high melting and boiling points. A few exceptions of group 1. All the exceptions of group 1 and a few exceptions from group 2. So we give all of these properties. And let me tell you, if you're supposed to talk about all of these properties, it is actually reasoned with two things. One, their regular, tightly packed arrangement. Two, the stronger forces of attraction between the cations and the delocalized electrons. All right?
Yes, sir.
Okay, moving on. We have discussed the properties of metals such as their malleability. All right. I hope you understand that malleability is about converting them into sheets by simply hammering them. They can change their shapes. We can change their shapes by hammering them, or ductility, which means you can pull them into wires. All right. Both of these properties actually depend upon their regular lattice. The layers are movable when forces are applied on them. Then we have sonorous. Whenever they are struck, they produce a loud sound. Then they have shine, or we also use the word luster. They are lustrous. They have a proper metallic shine. Now, shine is associated to these electrons, right? And sonority is also associated to the part given above, that their layers have the capability to move, to slide past over one another if we hit them strongly with a force. All right. So I should be actually giving this point over here, not this one. Okay. So when I talk about metals, I talk about all of these properties. There are two more properties to discuss, and I would like to discuss them separately. One of them is heat conductivity. All right. Heat conductivity is that when we heat one part of the metal, heat travels through the whole of the metal, and it is completely get heat up. And that's because from one point to another point, the heat can travel, and that can travel because of the to and fro vibrations of atoms. Then the second part is actually electrical conductivity, right? And electrical conductivity is all about electrons that can move throughout the system. Since electrons are very small charged particles that can freely move throughout the system, around the system, electrical conductivity is all about charged particles moving extremely fast. So these are all the properties of metal. And remember, we can reason every property in this portion with this structure. So you should be capable of relating a property to the appropriate reasoning behind it. This is considered as something that you must have done in IGCSE. All right. Another thing
Yes, sir.
that you should know from IGCSE, sometimes the student asks me that this is positively charged, this is positively charged, these are all positively charged. So won't there be any repulsions? And when I talk about negative charges, these are all negative charges. So won't there be any forces of repulsions? Then I usually talk to my students in such a way that I say that if this is a positively charged cation, and there is another positively charged cation right next to it, let's call this one as A and this one as B, and there are just two electrons. Let's say there is one electron over here, we call it 1, and there is another electron over here, we call it 2. And if I talk about the repulsive forces, I would only be able to count two forces, A with B and 1 with 2, since positive repels positive and negative repels negative, right? And if I count all the attractive forces, that would be A with 2, then A with 1, then B with 2, and then B with 1. So you would notice that if I take just two of each type of particles, even then I am able to tell you that there are more attractive forces as compared to the repulsive ones, which that is what makes the whole structure so stable, so strong, so hard, so dense, so having such a high melting and a boiling point. I'm talking about just two of each type of particles. Imagine if there would be Avogadro's numbers of each types of particles in just a few grams of the material. Not millions, not billions, not trillions, not quadrillions. Avogadro's number of particles in just a few grams of any metal that we compare over here for the sake of argument. So attractive forces हमेशा repulsive forces को high huge numbers से dominate करेंगी, keeping the fact under understanding that all of these positive ions will be able to attract all of these negative ions at the same time, and vice versa, in a specific area or in a specific part of the diagram under consideration, right? I hope you get the
Yes,
point,
sir.
right?
Yes.
Good, good. So A-level examiner assume that you understand both of these parts, which I wrote at left and at right, that you understand all of this and can reason about any of these points. Moving on, electrostatic attraction acts in all directions. The strength of metallic bonding increases with increasing positive charge on the ions. So of course, uh, the ones that have a higher positive charge can have a higher strength. Hence, our transition elements have a stronger impact in them with a higher strength of metallic bonding than we have in group 1 or group 2 elements, specifically the ones on top. Then decreasing size of metal ions in the lattice also increases the strength of metallic bonding. So smaller the ion and larger the charge, of course, greater the strength of the metallic bonding. That's why when we go down the group, the metallic character increases. I hope you remember from the example of group 1 that we have been doing back in IGCSE that if we talk about group 1 elements and we talk about their reactivity, we talk about their metallic character, as we go top to bottom, this is not as a good metal as this one is. This one would be a better metallic character, a stronger metallic sense, or greater metallic reactivity. And of course, increasing number of mobile electrons per atom also gives us the same idea about the strength of metallic bonding. So transition elements, since they can lose a lot more number of electrons than what group 1 elements do, so they have a higher strength of metallic bonding in them. That way, you can compare any two metals in terms of the strength of their metallic bonding. Can you?
Yes, sir.
Good, good. Moving on. Metallic bonding and properties of metals. Most metals have high melting and boiling points. It takes a lot of energy to weaken the strong attractive forces between metal ions, delocalized electrons. I've already explained that. They can only be overcome at high temperature. However, mercury is a liquid because some of the electrons in mercury atom are bound more tightly than usual to the nucleus, weakening the metallic bond between atoms. If the electrons are too tightly bound and they won't be easily lost, of course, that won't be a good metal or a metal with a higher melting or a boiling point. Mercury is one of those examples. Remember, we do not cater the fact about mercury being a liquid any more than what's written in these lines. So you're not going to prepare any more detail to this fact than this given line. That's about it. And let me tell you, this question hasn't been a past paper question uh, in like past 5 to 8 years or 10 years. They haven't been talking about mercury in specific. So you would rarely see it as a past paper question, rarely. Moving on, metals conduct electricity. Whenever a voltage is applied to a piece of metal, the electric current flows because the delocalized electrons are free to move. Metallic bonding is the only type of bonding that allows us to predict reliably whether a solid will conduct electricity, or there are types of bondings don't. Covalent solids cannot conduct electricity, but because none of their electrons are free to move throughout the structure. Graphite is an exception. Ionic solids cannot conduct because neither of their electrons nor their ions are free to move from place to place. So at the same time, when he was talking about metallic bonds and metallic solids, he considered covalent and ionic solids at the same time. This is all from IGCSE, nothing different. I hope you understand every part of it, right?
Yes, sir.
Now, any question like this which relates the use to the properties can be answered by simple understanding. You don't need any extra pieces of information. Take a look at question number 9, part B. The thermoconductivity of stainless steel is 82 webs per meter per Kelvin. This is a unit you may not be familiar with. That's fine, right? The thermal conductivity of copper is 400 of the same units. Why do some stainless steel saucepans have a copper base? In order to make them better conductors. The better conductor it is, the quickly it would be able to cook food, and hence we're going to consider it as a good saucepan, right? So you don't need to have any extra information. Questions like these can always be answered by the pieces of information you already have. Metals conduct heat. This is partly due to the movement of delocalized electrons. This portion is very small. Keep that in mind. It's mainly due to the vibration passed on from one metal ion to the next. as we have discussed before. All right, moving on. That actually finishes up metallic bonding. Oh, I thought the chapter is going to end. We still have intermolecular forces to do. Let's start with intermolecular forces, right? Intermolecular forces are different than bonding. Bonding forms molecules. When molecules are formed, they may have some attractive forces or repulsive forces between them. Those attractive or repulsive forces between the molecules are known as intermolecular forces. So, forces within molecules due to covalent bonding are strong. They are actually intramolecular forces. Instead of calling them intramolecular forces, we call them bonding. So intramolecular forces and bonding is the same thing. However, the forces between molecules are much weaker. We call all of these forces as combined as van der Waals forces or intermolecular forces. There are more than two types of van der Waals forces, but we're going to start off with two. All right. The first one is instantaneous or temporary dipole-induced dipole forces. We are going to call them IDID forces, or London dispersion forces is a more common name. The other type is going to be permanent dipole, or PDPD forces, which is further bifurcated into two types, PDPD itself and hydrogen bonding. So a special case of PDPD forces is hydrogen bonding. This occurs between molecules where hydrogen is bonded to a highly electronegative atom, and we're going to discuss that a little later in the same portion of the book. Remember that van der Waals forces is a general term used for all intermolecular forces, including ID, PDPD, and hydrogen bonding. There are more types to it, but we're going to discuss them later in parts of this book in AS as well as in A2. So there are more van der Waals forces, but it's just that we're starting off with two types, or including the hydrogen subtype, three types actually. Okay, so let's compare them a little bit to give you an idea where intra or intermolecular forces stand if we compare them all on one pattern. If we compare them all in terms of their bond strength, in terms of the units of kilojoules per mole, ionic bonding in sodium chloride is 760 kilojoules per mole. That in OH bonds of covalent bonding in water is 464. Hydrogen bonding, a certain PDPD type that we are about to do, is 20 to 50. A simple PDPD or permanent dipole force is going to be 5 to 20. And the instantaneous dipole versus instantaneous or temporary dipole or London dispersion forces or IDID forces is going to be 1 to 20. So this gives us a very good idea how the types of bonding or intermolecular forces compare to one another in terms of strength. All right? But remember, we're talking about a single bond or a single type of force. If you're going to combine a lot of numbers of similar type of force, you may end up with having a stronger impact than a certain type. Get the point?
Yes, sir.
It's like when there is a dead body of an animal, even the animal's huge, and a huge army of ants come around and they try eating him up since it's dead. So, what would happen? That force, that animal, that insect is too small, but since they are huge in number, they still would be able to consume the whole thing. So when PDPD forces or IDID forces are greater in number, their impact may be multiplied to have a huge effect as a whole. So keep that in mind that we're comparing forces individually, and an overall impact may include the number of forces we're considering at one point. So keep an open mind and uh, don't forget this factor, since we're going to face this factor a lot in the upcoming examples on the upcoming pages. Let's move on, right? I hope I made my point clear.
Yes, sir.
Good,
Yes.
good. Moving on. Electronegativity is something we need to know before we talk about these kinds of forces or bond polarity. So let's define electronegativity first. I hope you remember when we were talking about covalent bonding or different types of bonding, I was coming up with an example of two friends sharing their pocket money in order to get a burger from school canteen. I was talking about loss, I was talking about gain, I was talking about equal sharing. Then I also gave an example of unequal sharing. I told you that we humans are very much capable of going with some kind of unequal sharing, and that is you first decide to share equal amount of your pocket money to get a burger, and you do so, you get a burger. But when the time comes to divide the burger in exact half between the friends, one of the friends who is actually a little bit stronger takes the bigger piece of the burger just so because he thinks that he's stronger than the other. I hope you might have seen it already. We also call that a part of bullying. We also call that a part of teasing friendship. Whatever you might have faced already, I hope you know about that. And since I have been stating all along that we behave like our atoms behave like us, so this is something that we have seen in atoms. Now let's clarify the strength of one atom over another and claiming the part of electrons to do so. So electronegativity is the power of a particular atom that is covalently bonded to another atom already, but it attracts the bonded pair of electrons towards itself. Okay, let me give you an example. Hydrogen and hydrogen share a piece electrons to form a hydrogen bond in a molecule of hydrogen. Chlorine does the same, and I'm not drawing all extra electrons. In fact, let's just draw those since that would be good for concepts. So let's just draw all the outer shell electrons in a in a chlorine molecule. And then there is another example of HCl in which we have this kind of bonding drawn for their outer shells. Now imagine both the hydrogen atoms have equal number of protons in their nuclei to attract this shared pair of electrons to itself. So actually, since they have same nuclear charge, since they have same number of protons, the force on this bonded pair would be the same from both sides. What would be the result? There would be no one side claiming the covalently bonded or this bond pair for itself. Same happens in this chlorine case. But it's somewhat different for this HCl. Notice, if I start writing the number of protons on every individual side, you would automatically understand why one side prevails over another in claiming this bonded pair all to itself. So what happens in this case is that we call chlorine more electronegative atom since it has the capability in this kind of bond to attract the shared pair, a pair that has already been shared, a covalent bond that has already been formed to itself, towards itself. So we call that electronegative. The phenomenon is then known as electronegativity. Clear enough?
Yes, sir.
So it's pretty obvious. If there are two different atoms, they're sharing an electron, the nuclear charge for them is supposed to be different since they're different atoms. And if nuclear charge is different, the force that would be applied on the bonding pair will not be the same. So of course, one of them would be more electronegative and one of them would be less electronegative. Moving on with the text. The greater the value of electronegativity, the greater the power of an atom to attract the electrons in a covalent bond towards itself. For groups 1 to 17, the pattern of electronegativity is electronegativity increases across the period from group 1 to group 17, which means from left to right in a period, and electronegativity increases from bottom to top in every group, which gives us the idea that fluorine would be the most electronegative element since we're excluding group 18. So fluorine is placed on the extreme right and extreme top of group 17 to become the most electronegative element. on the planet. For the most electronegative elements, the order of electronegativity is something like this. And then I asked my students that you may write C, you may write H, and you may write I over here, since they have two close values to one another for electronegativity. And extend this rule a little bit for any questions that you might come across in past papers regarding more elements than what's given in the book. And also, that's mentioned below this rule, carbon and hydrogen have electronegativities that are lower than most of other non-metallic elements. So sometimes what teachers do is that they don't quote it like this. They instead only write iodine over here, and then they write carbon and hydrogen over there. Both ways, that is considered as correct. Since past papers is not going to differentiate between these three, so it's easy whether you put all three of these after bromine or whether you differentiate iodine and then put carbon and hydrogen after. It means the same thing. So fluorine is the most electronegative element, then comes oxygen, then comes nitrogen, then comes chlorine, so on and so forth. Make sure you memorize this rule with the added elements, so that it's easier for you to discuss electronegativity or its effects in the topics about to come. So which factors actually influence electronegativity in the periodic table? So those factors are always like the same. We always discuss three factors: nuclear charge, atomic radii, and shielding effect. Nuclear charge is actually the number of protons in the nucleus of an atom. Atoms in the same period with a greater positive nuclear charge are more likely to attract the bonding pair of electrons. Hence, the ones on right have more protons. If I compare, let's say I compare lithium with fluorine, since both of them are present in period 2, this one has 3 protons and this one has 9 protons. So, of course, this big difference would certainly clarify how fluorine is capable of attracting the bonded pair towards itself more than any other element on the same period. Make sense?
Yes, sir.
Moving on, atomic radius, or the distance between the outermost electron and the nucleus. Atoms in the same group in which outer electrons are further from the nucleus are less likely to attract the bonded pair of electrons because the pull of the positive nucleus on the electron pair is lower. All right. So since they are far away, the pull will be less because of the distance. Shielding effect. The greater number of inner electron shells and subshells, the lower the effective nuclear charge. On the bonding electrons. So the more are the shells, inner shells filled, the lower will be the effect of nuclear charge on the bonding electrons. This means going with lower periods, period 3, period 4, period 5, so on and so forth, there would be less and less attraction. That's why up the group, the value increases. The first one tend to explain the left to right period rule. The last one tends to explain the bottom to top increase rule. The center one explains both the left to right and bottom to top increase rule. So whichever one they're asking about, you can actually go with that specific reasoning point. Sometimes students tend to write all three of them, given the space is enough for all three of these. That's a great idea. Make sense?
Yes, sir.
Moving on, Ionic or covalent. Now, the most commonly used scale of electronegativity values called the Pauling electronegativity scale, which we call also NP, which gives the values. And since these are the values for the normal elements of period 2 and period 3, this one is period 2, this one is period 3, and we have only considered normal elements since they also have just normal elements. So from lithium to fluorine and from sodium to chlorine. you would automatically be able to put carbon beneath all of these, right? Because of this table. Now, let's clear a few points out. Carbon and hydrogen have 2.5 and 2.1 electronegativities, and that is lower with most of the other non-metallic elements. Falling electronegativity values have no units. Difference of electronegativity values are actually very beneficial for us. This is something that the teachers used to tell the students, but was not a part of previous books. That has been added to the books. Teachers used to ask the students to write it on the book, since that was a part of past papers, but that wasn't part of textbooks properly. But now it is. And it's a very good point at that. If the electronegativity difference values between two elements is high, for example, 2 or more, that compound is more likely to be ionic. Since this one is 0.9, this one is 3.0, the difference is 2.1. The compound is ionic. Sodium chloride is ionic since the difference is 2 or more. If the electronegativity difference is lower, example, below 1, the compound is likely to be covalent. This and this is 0.4, the compound is supposed to be covalent. A zero value shows there is no ionic character in the bond at all, which brings us to a point that an ionic compound may have a slightly covalent character just because the electronegativity value is somewhat closer to 1. Or a covalent compound may have some ionic character just because the electronegativity value is closer to 2 but less than 2. A bond will have no ionic character if the answer is 0. So ClCl or any bond which is made up of similar atoms has no ionic character at all. We call them pure covalent compounds. Since the electronegativity difference for any of those compounds, be it the molecule of hydrogen, the molecule of fluorine, the molecule of oxygen, the molecule of nitrogen, the molecule of bromine, the list goes on for any type of molecules which is made up of similar elements, be it P4, be it S8, whatever that is. So some compounds are not entirely covalent and have some ionic connector. Some compounds are not completely ionic, may have some covalent character. These have intermediate electronegativity difference values, for example, 1. I actually tend to say that from 1 to 1.5 is ionic having a little bit of a covalent character. Sorry, covalent having a little bit of an ionic character. In between 1.5 to 1.8, 1.7, you would find ionic having a more of a little bit of covalent character. So we use the word predominance. Closer to 1, predominantly covalent. Closer to 2, predominantly ionic. Predominantly ionic means mostly ionic, little bit of covalent character. Predominantly covalent means mostly covalent, a little bit of ionic character. One of these would be explained in AS, the other one in A2. All right. Which one are we going to explain right now? The covalents that have a little bit of an ionic character are the ones that we're going to start with and explain them over here. The ones that are ionic and have a little bit of a covalent character is the one that we're going to keep for A2. Let's start with the topic polarity in molecules. Any questions from the previous one before I move on?
No, sir.
Okay. Polarity in molecules. Now, when the electronegativity of two values or difference of two atoms forming a covalent bond is same, the pair of electrons is equally shared. I've given a lot of examples: fluorine, chlorine, hydrogen, bromine, iodine, the list goes on, are called as non-polar bonds. There is no polarity. There is no slightly ionic character in them, right? When a covalent bond forms between two atoms that have different electronegativity values, the more electronegative atom tends to attract the pair of electrons towards itself. As a result, what happens? The center of positive charge does not coincide with the center of negative charge. we say the electronic distribution is asymmetric and the two atoms are partially charged. What do? We write delta positive or partial positive. This is also pronounced as delta. This sign is also pronounced as partial. Partial positive charge on the less electronegative atom and partial negative charge on the more electronegative atom. Let's do it for HCl. So, since I have been talking about that example since the previous page, okay? Now, what would happen is that instead of being in the exact center of these two, this bond would move a little bit closer over here, closer to this one and farther from this one. This is what seems to the atoms. Actually, that's not the fact that it moves closer. This is what in we can call an easier imagination for student. What happens is that this shared pair has to revolve over chlorine and over hydrogen. Since the via of hydrogen being a smaller atom is small, so they take very less time to move over hydrogen, and they take some more time to move over chlorine, since chlorine is a much bigger atom as compared to hydrogen. So what happens that it spends more time on chlorine, giving chlorine the more surety of having the both electrons with itself and giving less surety and less time to hydrogen. That's why what we generally say is that the bond literally moves a little bit over there since it spends more time over chlorine. So what do? When we draw a covalent bond, we draw signs, partial positive, partial negative. These signs automatically give the idea to the reader that electronic distribution is asymmetric. It's not balanced anymore. The atoms are partially charged. Since this pair of electrons spends more time with chlorine, the chlorine is slightly negatively charged, and the hydrogen is slightly or partially positively charged, hence these signs in these words. All in all, what we say is that the bond is polar. It has a dipole. Di mean two, pole mean portions. So just like Earth has two poles, the North Pole and the South Pole, this molecule will have two poles. This one as slightly having a negative charge, this one slightly having a positive charge. They don't have complete positive and complete negative charge, since that's a much bigger value. They only have a partial value of charge. All right.
Yes, sir.
Let's take a look at the diagram in the book, since the diagram tells us the same thing, like this. And this diagram gives us one more idea. Difference in electronegativity of the atoms in a covalent bond increases, the bond becomes more polar. The degree of polarity of a molecule is measured as dipole moment. This is the degree of polarity. The direction of dipole is shown by this sign. It's an arrow with the plus sign at the other end. The arrow points to the partially negatively charged end, and the plus sign actually depicts the partially positively charged side. This depicts the positive sign, this depicts negative sign, means the electrons would be spending more time on this atom. All right. So this dipole
Yes, sir.
moment gives us the idea of degree of polarity of every molecule. We're not going to consider dipole moment in details about these molecules, but this is as far as we come for dipole moment. Moving on, what we need to discuss is that the molecules containing more than two atoms, we have to take into account about two things: the polarity of each bond and the arrangement of bonds in a molecule, which is more like a discussion for organic chemistry. So considering a couple of examples for organic chemistry, let's discuss both the points in detail. Since an organic molecule may have many bonds, different types, of course, so we need to discuss the polarity of each bond and the arrangement of bonds in the molecule. Trichloromethane, CHCl3, is a polar molecule. There are three CCl dipoles in the similar direction. Their combined effect is not cancelled by the polarity of CH bond, as shown in this diagram. This is because CH bond is virtually nonpolar. The difference between these two is 2.5 minus 2.1, which is 0.4, which not even consider it as polar. Let me take you back. Let me clarify my point. Remember this difference, 0.4 for carbon and hydrogen. Consider these values, a little more, 0.5. You would say, how come this 0.4 is almost nonpolar and this 0.5 has an effect? Consider it like a jump up. It's just a zero point 0.1 effect, but actually in atoms, it's more than what we need in kind of discussion like this. So yeah, 0.5 has an effect much more than 0.4 in this case. So there are three CCl dipoles in the similar direction. CH bond cannot nullify the effect, the combined effect. Of course, 0.5, 0.5, 0.5 has a total of an effect which 0.4 will not be able to cancel. Even if go with simple summing up and differentiation, there would be a big difference. The electronic distribution is asymmetric now. The bond is polar with a negative end towards the chlorine atoms. So these shared pairs will be moved slightly towards the partially negatively charged systems, right? This gives us an idea about any of the organic molecules we want to compare in terms of electronegativity values. समझ रहे हैं? इन तीनों bonds के अंदर shared pairs chlorine की तरफ attracted होंगे. इस बॉन्ड में चूंकि इसकी इलेक्ट्रोनेगेटिविटी ज्यादा है, ये कार्बन की तरफ अट्रैक्ट होगा. ओवरऑल इस पूरे मॉलिक्यूल में हम इस तरह का इफेक्ट शो करते हैं, since all of it is going towards the side. All right?
Yes, sir.
Some molecules contain polar bonds but have no overall polarity. This is because the polar bonds in these molecules are arranged in such a fashion that the dipole moments cancel each other out. For example, is tetrachloromethane. It has four polar carbon CCl bonds pointing towards the four corners of tetrahedron. This points towards here, towards here, towards here, and unfortunately, this points towards here, which actually balance all of them. Now, you would consider how this one is capable of balancing all four of these. Let me tell you, this is a three-dimensional structure and not two-dimensional in order to easily sum them up. That's why I was just given an example of summing and differentiating the electronegativity values as the sake of an argument, but not actually doing that. So this becomes a nonpolar molecule, this becomes a polar molecule. This is a way to tell you how we discuss the polarity of bigger organic molecules, but this is not exactly measuring technique for all the molecules that you might face, since you won't be facing only tetrahedral molecules. You will be facing many other different types: trigonal, bipyramidal, the octahedrals, the squares, planars. You'll face a lot of things. So this is just an idea. Remember, the questions won't be difficult, won't be about other shapes, since you are incapable of calculating or measuring about with different shapes the dipole moments or their cancellation effects. So this is just an idea for you. You won't be facing questions like these. Make sense?
Yes, sir.
Good. Good. Moving on. Remember, not all molecules with polar bonds are polar molecules. Sometimes the polar bonds cancel each other out because the same types of bonds have dipoles pulling in opposite directions. A very good example for this one, there is a question in the past paper which discusses this exact line and then gives you an example of carbon dioxide and draws it like this, and then asks you why this molecule is nonpolar. Now, remember, these are polar bonds since the dipoles are drawn right on top of them. And since he has already given the hints that the polar bonds cancel each other's effects because the dipoles are pulling in exact opposite directions, which is actually an answer to this question. Make sense?
Yes, sir.
So the more this oxygen is attracting the shared pairs, since that's a double bond towards itself, in the exact opposite direction, the other oxygen atom is doing the same, canceling each other's effects and making a structure containing polar bonds a nonpolar molecule, which gives you the idea that without having a proper knowledge, a proper detail, a proper examination of a molecule, you won't be able to call any molecule a polar or non-polar molecule based on the bonds it has. It might have polar bonds, but it might be a non-polar molecule. It might have no polar bonds, and still it's a non-polar molecule. Or it might have polar bonds and it's a polar molecule. So there are many chances. There are many different kinds of compounds. So what we do is that in order to determine the charge distribution in molecules and ions, we use a method known as X-ray spectroscopy. One method involves firing X-rays at molecules, measuring the energy of electrons given off. Using this method, scientists have found out that in sulfate ion, the sulfur atom has a charge of plus 1.12 units, and four oxygen atoms have a charge of minus 0.78 units. All right, which tells us that it may or may not be exactly polar or non-polar. I'm not discussing that since you won't be facing questions like these. I'm just giving you an idea what comes from this paragraph to your mind. You won't face a question with this paragraph. This is just to open new horizons for you. All right. Don't forget, if I talk about sulfate, it has structure like this. And hence, SO4 and these two negative charges, SO4 negative too. So of course, the forces over here or the forces over here would be balanced. The forces over here would be balanced. But we needed to know the exact units, and these are the units that we based. All right. So they discuss some other molecules, and just from their values given in the question, they ask you whether they are polar or not. Okay. These are as simple as the questions that you might face. So remember, the questions regarding these would be extremely simple. All right.
Yes, sir.
Okay. Moving on. I think let's stop right here.